Oh, hello. I thought we could look at assignment 77A. It's called Chapter 5, entire chapter review stuff. And there's a lot of stuff here. First thing I want to say is that problem, one actually was an old free response question, but that problem number 2, I think you should experience it, but there's nothing that hard on our test. Okay, problem number 1. You've got 100 feet of wire, and that's 100. You're going to cut that wire somewhere and turn some of this wire into square and some into a circle. Where do you cut the wire so that the combined area of the two shapes is a maximum? Okay. Ooh, where do you cut the wire so that the combined area will be a minimum? Interesting. So let's see what happens here. I think about my square, and this amount has to go here, 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 and here. So all of these sides should add up to that amount. Okay, so 4s should add up to x. Side length then is x over 4. And since we know the formula for area of a square is side squared, then I can take this side and square it. And so my area will be x over 4 squared. So the area of the square is x squared over 16. Now, what about the circle? Well, I've used up x feet of wire for the square, and so here for the circle, I've got 100 minus x feet that I can use. And for the circle, we're talking about making a circle from this piece of wire. This distance is 100 minus x. Well, that's what 2 pi r is. And I know the formula for area of a circle is pi r squared. So I really want to know what r is in terms of x. If I divide both sides by 2 pi, I see that radius is going to be 100 minus x all over 2 pi. So that's going to go in there. So area of a circle is pi times 100 minus x over 2 pi. Don't forget radius squared. And so now we've got the area of a circle in terms of x, and we have the area of the square in terms of x. And we're talking here about the combined area being a minimum or a maximum. So let's say, oh, by the way, this notion of using x for the perimeter of the square, you could have said x was the circumference of the circle, and you should get the same answer. And at one point I might have known which one of those would have been easier before I started the problem, but today I don't. So I'm just going with what came up first. Okay, so we've got area of the square is x squared over 16, and area of the circle is, well, we could tidy this up. We've got 100 minus x squared on top. And if I square here, I have 4 pi squared. And that pi will cancel. So I'm thinking that the area of the circle, then, is going to be 100 minus x squared over 4. Okay? Okay, so let's think about combined area. Combined area is going to be the area of the square plus the area of the circle. And that's going to be x squared over 16 plus 100 minus x squared over 4. And instead of making that a fraction, you might want to bring that 1/4 out in front like that. So now I want combined area prime. So I bring down the 2 over 16 is going to be 1x plus, bring down the 2 over 4 is 1/2, 100 minus x subtract 1 times the derivative of the inside function. Okay, and so now that's going to be 1/8 x minus, well, half of 100 is 50 times -1, -50, and negative is a positive 1/2 x. That's 4/8 plus 1/8 is 5/8. 5/8 x minus 50 is a prime. Well, this linear equation is never undefined, so I don't have to worry about that. But I could set this equal to 0, and then I'll have 5/8 x equals 50. If I multiply both sides by 8 and divide both sides by 5, I end up with x equals 80. Okay, so that's a critical point. But you know, there's more places to find maxes and mins than just a prime equal to 0. There's, of course, a prime undefined, and we already went through that and said this linear equation is never undefined, but we also have the endpoints of a bounded interval. And this 100-foot piece of wire, yeah, well, that's bounded, so you can't have less than 0 or more than 100. And remember, we said that this is what x is. We said that x was going to be 4s, and so s would be 20. So when the side of the square is 20, what do we get? Well, I can find that out, but here, what does it say? It says, where do you cut the wire? It doesn't care what the area of the square and the circle are, so I'm not going to go down that road. I'm just going to say that when x equals 80, something's happening on A prime. So let's see what's happening on A prime. If I put a 0 in for x, I get negative over here. And if I put 100 in for x, 100 divided by 8? No, I want something divisible by 8. 200 divided by 8. 200 divided by 8 is 25. 25 times 5 is 125 minus 50. That's positive 75. So I see here at x equals 80, that's going to be a min. The combined total, the combined area is a min when x equals 80, because to the left of x equals 80, A prime is less than 0, and to the right of x equals 80, A prime is greater than 0. Well, that's great, except the first part of the problem said, where's the maximum? And I don't have a maximum. Or do I? And this was, of course, the reason why all those kids were so terribly, terribly, terribly upset with the College Board the year they saw this problem show up, because it turns out that when x equals 0, we have a maximum. Look, A prime is negative here as well, which means from x equals 0 on, our area function is decreasing. Well, that means that this is a maximum here. And after 80, A prime is positive, so area is increasing until we get to 100. So that's also a max. Okay, so I need to figure out which of these is the absolute max. Remember, x was what we were putting in for square, okay? And we had area of the square was x squared over 16, as I recall. And area of the circle, what was that? 100 minus x over 2 pi squared. No, it wasn't, because there was a pi out there. Pi radius squared. And then we canceled, and we said that was going to be 100 minus x squared over 4 pi. So 1 over 4 pi. Okay, so there's my circle. And what did we say about a prime? We don't have to worry about a prime. Actually, I want to plug the values in, these values, the endpoint values, into the original function, like we did in section 5.1, where we're using the extreme value theorem to evaluate which of these maxes would be bigger. So if I plug a 0 in for x, this goes away. And that goes away. And so I'm left with 100 squared over 4 pi. Where's that pi? Oh, no, that pi. Okay. So that's my combined area when x equals 0. What about when x equals 100? Well, look what happens if you plug a 100 in. 100 minus 100 is 0. That goes away. And I've got 100 squared over 16. So tops are the same, bottoms are different. So which of these is bigger? Well, this is 10,000 divided by a smaller number here than here. This is 4 times 3-ish, so 14. This is 16. So let's just confirm that 10,000 divided by parentheses 4 pi is going to give me 795.775. And 10,000 divided by 16 is going to give me 625. And what was it when we had at 80? Oh, we had a min, so I don't really care. Though I kind of care. It was when x was 80, so 80 squared divided by 16, it's going to be 400, plus 100 minus 80 is 20, 20 squared is 400, I have 400 times pi divided by 4 pi squared. And that gives me a smaller number than I had imagined. And so rather than go down that rabbit hole, I'm just going to compare these two. And what I notice is that when x equals 0, I have my maximum area. Now, what does that mean, x equals 0? Well, x was the amount that we used for the square. And so this tells me don't make a square. Don't make a square, just make a circle. This number is as large as it is because we're using all of the wire for the circle. When we use all of the wire for the circle and none of the wire for the square, we maximize our combined area. And students that year were kind of livid because they had the impression at the beginning of the problem that you were going to end up with two objects, a square and a circle, and then when you added those areas together, you would get a maximum at some point. And to have it actually be that, no, don't cut the wire, turn all of it into a circle and none of it for the square, yeah, that made a lot of them upset. So here you go. That can happen. All right, that was a bit. Now, the hard problem, number 2. Again, nothing this hard on our test. So we've got this very interesting corral. It's got a semicircle and a rectangle. And we're told that the sides of the semicircle are y's, and we know that this is x. I know that that man is dead. Oh, the things you can know. So this diameter up here is going to be x, which means that that radius is x over 2. All right, so what do we know? You have 600 feet of fencing to make the outside of this corral. That does not include this piece here. So we're going to have x plus 2y's plus, well, how much fencing do I need for that? Well, this is a semicircle, and I know the formula for a circumference of a circle. Circumference is 2 pi r, but I only want the circumference of half a circle, and so that's going to be pi r. Okay, pi, oh, and what did we say r was? X over 2. So x over 2. All right, so we've got an x. We've got pi r because we want half of the circumference. There's pi r. Radius has been replaced with an x thing. We've got these two y's, and we have this x. Fabulous. And how much fencing did we have for that? That is 600. And that's our helping equation. Ew, Mr. Kukla. Yeah. And what do you want to solve it for? I kind of want to solve it for y. Because there's a bunch of x things that just aren't gonna combine here. So yeah, I'm probably thinking about y, though maybe you're thinking about x, and we should end up with the same answer when we're done. We do want to find the dimensions that maximize area, and we know that the area here is simply x, y, but we've also got the area here, and that's half a circle. So 1/2 pi. What was our radius? X over 2 squared. So pi radius squared is the area of the circle, but we only want half of that. In fact, that's going to be x squared over 4 times 2, so I have pi over 8x squared, and here I have xy. So there's area, total area. Still got a y here. Got some x's, that's good, but I got a y and I got to get rid of the y, so I'm using this helping equation. 600 minus x minus pi over 2x equals 2y. And if we divide everywhere by 2, this will be a 4, this will be a 2, and that'll be a 300. 300 minus 1/2 x minus pi over 4x equals y. And so that's what I want to put in here. Okay, don't lose that pi over 8x squared that you'll want later. So this is going to be 300 minus 1/2 x minus pi over 4x plus 1/8 x squared. Oh, there's a pi on top. So there's a pi on top. That's the circle, that's the rectangle, that's us getting rid of, and we have pi there because that's part of the 600. Okay, sorry, just need to think about that a minute. So I'm going to distribute this x and see if I can combine some like terms before I take the derivative. So now I've got 300 x minus 1/2 x squared minus pi over 4x squared plus pi over 8x squared. That's my area. Still haven't taken derivatives, still haven't done any calculus, just doing some pre-cal, some trig, no, not trig, some geometry. Minus 2 pi over 8 plus 1 pi over 8 is going to give me 300x minus 1/2 x squared minus pi over 8x squared. There's area, all in terms of x. And this pen is dead too. So where are the more pens? That one's dead. Oh no. There's a paucity of pens. Yay, I found some more. Okay, so now I'm ready to take the derivative here. A prime is going to be 300 minus the 2 comes down x, the 2 comes down pi over 4x. Okay, so this derivative is never undefined. Let's figure out when a prime is equal to 0. So 300 minus x minus pi over 4x equals 0. And we get 300 equals x plus pi over 4x. And I notice that both of these terms have an x, so I'm going to factor out an x. And to get x by itself, I want to divide both sides by 1 plus pi over 4. 1 plus pi over 4. Okay, so Don't forget parentheses in the denominator. In my calculator, I'm typing in 300 divided by parentheses 1 plus pi over 4. And I end up with 168.0297. I'm going to go with 03. Okay, so that's my x value. And when I take that x value and put that x value 168.03 on an A prime sign chart, and conveniently I still have A prime here, and I want to put something in over here and something in over here. Well, if I plug a 0 in, I get a positive 300. And if I put in something bigger than 168, I don't know, how about 300? 300 minus 300 goes away, and now I've got 300 times this, and that's a negative, so I've got a negative there. All right, so it looks like, indeed, area is a max when this is what x is equal. And do we have to find y? Yes, because we want the dimensions. Well, remember that we said y was equal to, goodness me, is that y? No, I don't think it is. I think I've erased it. So I'm going to let you find y by going back to find what was it that we said about y. It's part of the perimeter. Remember, there was x plus 2y plus, that was half a circle, pi r is x over 2, and so we have 2 for all the way around. We don't want all the way around, we just want this, and so pi over 2x, and that was 600. And so we subtracted these things and divided by 2 to get y, and it's in here that I'm going to plug my x value to figure out what y should be. Okay, but I'm going to let you do that because this video is way too long already. There's only 2 problems. Oh my goodness. Let's see if we can move along. Hey, I do want to say that differentials, wow, if you don't practice these differential problems here, number 3, number 4, number 5, number 6, those are all differential problems, and if you don't practice them, you probably aren't going to be able to do the problem on the test because you will have forgotten them. Not because they're hard, just because you will have forgotten them. So let's go through these. Number 3 says we've got a revenue function, dollars, in terms of x, and x is the cost of the monthly pass. Okay, so that's going to be 1.5x minus 0.01x squared. And what are we looking for? Estimate the change in revenue. Remember, we don't want the exact change in revenue, right? The exact change in revenue is going to be R of 53 minus R of 50. We do not want that. That is the exact change in revenue. We want DR, the approximate change in revenue. And I don't know if you recall, but this starts with us saying, okay, I got this R function, and I want to take the derivative with respect to x. And so I take the derivative over here with respect to x. You might call that R prime over there. I'm going to call it 1.5 minus 0.02x. Okay? And then I'm going to multiply both sides by the differential dx. So there's dr. That's estimating the change in r. dr equals 1.5 minus 0.02x times dx. Well, what do we know? We know that the change in cost of the pass goes from 50 to 53. So we know that dx, the change in x, is exactly 3. And we would be building this tangent line at the at this point here at 50 bit, and so I'm going to plug in 50 and a 3. Okay, so let's think about this. This is 2 over 100, and that will cancel, leaving me a 2 on the bottom, and those will cancel, leaving me 1. 1.5 minus 1 is 1/2 times 3. My dr is 3 over 2. Well, what does that mean in the context here? Well, it means that, what were our units? Dollars. Dollars. So when we raise the price from 50 to 53, the approximate change in revenue is going to be $1.50. Is it really just dollars? It really is just dollars. Okay. 4. 4 says, estimate the change in surface area and the change in volume of a sphere whose radius is 6 and dr equals 0.3. And there's actually two problems here, right? There's the surface area problem. Area is 4 pi r cubed, no, squared, because that's the area of a sphere. We're doing sphere. Yes. And we've also got volume of the sphere, which is 4/3 pi r cubed. Okay, so I want to estimate the change in area. So I want ADR equals 8 pi r multiplied by dr. So the change in area is going to be 8 pi r dr. Well, we're told that r is 6. So 8 pi times 6 times, and we're told that dr is 0.3, which I'm going to write as 3/10. So what do we have? Well, I can take a 2 out of there. I'm going to have 9 times 8, which is 72 pi over 5. And that's our estimate of dA. Change in area, so this is going to be inches squared. So when radius is 6 and the change in radius is was it 0.3 or 0.03? Oh, yes, I did 3 over 10. So these are inches squared. We're going to have a 72 pi over 5 square inch change in area. We can do something similar over here where we take the derivative of both sides with respect to r. And so we know that dv is 4 pi r squared dr. Again, we're going to plug in our radius and our dr. 4 pi times 36, because 6 squared. And dr was 0.3 or 3/10. So we're going to take that 2 out of there. And I'm going to have 72 times 3. Is that 216? Yes, it is. So I've got 216 pi over 5, and these are going to be inches cubed because we're talking about a change in volume. Okey-doke. Problem number 5. Oh, the 9th ring of hell. How accurately must the side of an isosceles right triangle? Oh, it's isosceles. Thank goodness. I was worried that it was going to be equilateral. How must it be? So how accurately must the side be? Which the side is x, so we're talking about dx. What do we know about dx? It measured if its area must be within 0.05. Actually, that's the change in area. Must be within, is it 0.5%? So that's 1%. We want half of that. So 0.5%, looks like that, of the actual area. Okay, and so that's what I have. Well, I know that the area of this triangle is 1/2 x squared, and I know that dA dx is going to be x, and so dA is x dx. Well, look, dA is 0.005a, so I can replace this with 0.005a. And you might be saying, well, how does that help me? Psst, what's the area? Plug it in. So that's going to bring me to 0.005 times 1/2 x squared should equal x dx. All right, well, let's see what we know. If we divide both sides by x, this will cancel one of those. I'm taking this and cutting it in half. So I'm going to have 0.0025 x equals dx. So what does that tell me? What is it that I know? Well, I know the error in measuring the side length must be within 0.25% of times the actual side length. Right? Right. It's funny how this part about turning this number into a percent is often the hardest part for people who've gotten this far. All right, and 6. How much error in the square can? Oh, how much error can there be in the area of a square if the side of the square is measured, the error in square is measured within 0.5% of the actual value. And that's the value of the side length. Okay, so we know that ds is 0.005s, and we want to know about dA. Well, I know for a square, area equals side squared. And so dA ds is going to be 2s. And therefore dA is going to be 2s ds. Well, we know that ds is this. So we're going to say 2s times 0.005s. If I double this number, I'm going to get 0.01. And s times s is s squared. So that's dA. But remember, the area is s squared. So where I see s squared, I can plug in a. The error in area is 1% of the actual area. And this is, of course, our estimate. The estimate of error in area will be within 1%, 0.01, of the actual area. And that's minimally what I would write. I'd probably want to go along and then say when the side length is measured way out of room, within 0.5% of side length's actual value. All right, number 7. We're almost halfway there. 7 says, you have a rectangular basin filling at 3 cubic feet per minute. Hey, if I name that calculously, I'm going to call that a dVdt. And as you watch you fill, you wonder, how fast is the water level rising? We wonder what dH dt is. Your basin has a side length of 3 feet, and I think that's supposed to say a depth. Oh, it's a rectangular basin. Okay, so I've got a basin. My basin. And this is 3, and this is 2. Oh, isn't that interesting? My basin has fixed side lengths. So the only thing that's varying is the height. And, if I write the volume for this basin, it's 2 times 3 times h, for 6h. If I take the derivative of both sides with respect to time, don't forget to take the derivative of that with respect to time, I end up with this. We've got a dV dt, 3 equals 6 dH dt. And if we divide both sides by 6, it seems like dH dt is 1/2. And that's a change in height, so we're going to have feet per minute. Nice. Oh, that was so gentle. 8. 8 says the rate at which water is entering a vertex down cone when h equals 5 and dH dt is 1 over 4. I'm going to say this is feet per second. The radius of the cone is 4, and the height of the cone is 10. All right, and this is going to be one of those similar triangle situations. 4 is to R as 10 is to H. I see a lot of DHs over here, so I really want to get R by itself. I'm going to have 4H equals 10R. And so that leads me to say that R equals 2/5 H. So now when I consider the volume of the cone, 1/3 pi R squared H, I'm going to rewrite by getting rid of the R. Pi over 3, 2/5 H squared times H. Right? We're replacing this R with what R is equal to. We still have that H. So it's going to be 4 over 25, or pi over 75. Wait a second. 4 pi over 75, h to the third. There's our volume. If we take the derivative of this with respect to time, we're going to have v dt equals, the 3 will come down and cancel, 4 pi over 25 h squared. Don't forget the dH dt. Now we're ready to plug in the changing quantity and the dH dt. So I've got 4 pi over 25 times h squared, which is 25, times dH dt, which is 1/4. Well, isn't that tidy? Pi. dV dt is pi. And what are the units? We're looking at feet per second. So this is going to be pi feet cubed per second is our change in volume. All right. That's the rate at which water is entering our vertex down cone. All right, next. 9. Ooh, it's a ladder problem. Remember, when you head towards the intersection, rates are negative. And when you head away from the intersection, rates are positive. In problem number 8, we've got a building and a 20-foot ladder. By the way, the ladder is not changing its length. That is a constant. I plug constants in before I take the derivative. I plug changing quantities in afterwards. All right, let's see what we got here. The building starts to slide away from the wall, dx dt. The height of the top of the ladder is a function of time such that at time equal to 0, we have 12 feet. So that's a 12. And we're given that dH dt, the change in this height, is -4, because the ladder will be sliding down towards the intersection. dx dt is going away from the intersection. X is getting bigger, so I expect dx dt to be positive. All right, and do we know something to relate all these elements? Sure, the Pythagorean theorem. I can say that hypotenuse squared should equal, this is a changing quantity, I do have to plug the variable h in there, plus x. Okay? I take the derivative of the constant is 0. This is going to be 2h dh dt. Remember, again, you're using chain rule. You're bringing that 2 down and you're leaving that inside alone. And then you're multiplying by the derivative of that inside with respect to time. So really, don't lose that, okay? So our height was 12, and dH dt was -4. And so we've got 2 times 12 times -4. That's going to be 24 times 4, 96, -96. is what? What did we just find? That's very interesting. Oh, I didn't finish the derivative. What a noob. 2x dx dt. All right. And we're looking for here, find out how far away from the wall the base is the moment and how fast it's sliding away. So we want to find both x and dx dt. Well, x is pretty easy because it's just doing the Pythagorean theorem. 20 squared equals 12 squared plus x squared. 400 minus 144 is x squared. Is that 256 equals x squared? Look at this. This is 3 times 4. This is 5 times 4. So I'm guessing that's 4 times 4, or 16. And that's in fact what I'm going to get for x when I take the square root of both sides. 3, 4, 5 right triangle. But in order to find what dx dt is, I'm going to need to plug in that 16 here, and in addition, this minus 96. So that 0 equals negative 96 plus 2 times 16 times dx dt. I'll add 96 to both sides, 32 dx dt. And if I divide by 32, I see that dx dt is equal to 3. I believe these are feet per second. All right, the ladder is sliding out at 3 feet per second when this 20-foot ladder is sliding down the wall. All right, that was 9. 10. A giant walks away from a lamppost. Giant lamppost. The tip of the shadow, ant. Oh, it's a giant ant. Ooh, this is an ant. The tip of the ant's shadow moves twice as fast as it does. Well, isn't that interesting? So the shadow is this. This is where the shadow is. And the ant, let's call this x, the ant is moving, well, I don't know which way the ant is moving, do I? Ant walks away. Ant is going this way. And so we're going to have a dx dt is going to be the ant moving away, and we're going to have a ds dt for the change in the rate of the shadow. And we're told something here that the shadow is twice as fast as the ant. So ds dt equals 2 times dx dt. And I imagine we're going to need that helping equation in a little bit. We are asked, how tall is the ant? So I want to find this. I know that this is 12 feet. All right, well, all I see here to use is similar triangles. So let's go to similar triangles. I'm going to have A is to 12 as S is to this whole side, right? Not just this part. This is the whole side of that big triangle. So we want this whole side here. That's x plus s. All right. So, yeah, I want to solve for that. Do I know this? I don't feel like I know that. I feel like I got too many unknowns here. I really want a helping equation. And I guess that's all I get for a helping equation is that. Well, if I cross multiply, I have ax plus as equals 12s. And if I take the derivative with respect to time, I'm going to have a times dx dt plus a times ds dt equals 12 times ds dt. And let's move this ds dt over there and give ourselves a little more space. So a dx dt equals 12 minus a ds dt. And what did we know? We knew that ds dt was 2 times dx dt. So let's go with 2 dx dt here. Oh look, we have dx dt on both sides. So I'm going to divide both sides by dx dt. Now I've got a equals 24 minus 2a, or 3a equals 24, or a equals 8. Wow, that was so tidy. I was so worried up here when I just took the derivative of my similar triangle proportion. Yeah, that is a big ant, 8 foot tall. Okay, what do we have next? 11 through 13, find when f is increasing, decreasing, concave up, concave down, maxes, mins, and inflection points. Oh my god, there's so much here. Okay, so problem number 11 says f equals x squared minus x to the 1/2. And therefore f prime is going to be 2x minus 1/2 x to the minus 1/2. And f double prime is going to be 2 plus 1/4 x to the minus 3/2. All right, well, I got an f prime. This f prime is undefined because remember 2x minus 1 over 2 root x, because I can't have a 0 in the denominator, nor can I have any negatives there. So I'm only looking at x values that are bigger than 0. Okay? All right. So if I set f prime equal to 0, I'm going to have 2x minus 1 over 2 root x is going to be 0, or 2x equals 1 over 2 root x. And if I multiply both sides by 2 root x, I'm going to have 4x root x equals 1. See that? Yeah, I don't want to write it like that. I want to write it as x to the 1/2 times x to the 1, which is going to give me x to the 3/2. I'm going to divide both sides by 4. And now, how do I get rid of this? Well, in pre-cal, we multiplied, we exponentiated 2/3 with the reciprocal power. So I get x equals 1/4 to the 2/3 power. You could certainly write this as 2 to the minus 2 raised to the 2/3 power, but I don't know if that's any more helpful than that. So, man. All right, and I squared both sides. So that makes this a must check. Ugh, really? So don't want to must check this. It's just going to be a nightmare, isn't it? Oh, why couldn't you be an 8? Because the cube root of 8 would be 2, and the 2 squared would be 4. It would be perfect. But no, you're not going to do that. So, let's go. We've got our f prime sign chart, and we seem to only have one critical value, and that was 1/4 to the 2/3. Okay, 25 raised to the 2/3 power. And I get that that's 0.397. 0.997. 397. Okay, 0. So how about I plug in something like, what's an easy square root? 0.25. That's one. So 0.25 is 1/4. Square root of 1/4 is 1/2. 1/2 times 2 is going to be 1. 1 over 1 is 1. So I've got minus 1. And then what was I plugging in here? I was plugging in 1/4. Yes. So 2 times 1/4 is 1/2. So 1/2 minus 1, that's definitely negative. And then over here, I've got, pretty sure it's going to be positive. Let's plug in that 1. 2 times 1 is 2. And if I plug in a 1 here, I have 1/2. So 2 minus 1/2 is definitely positive. So I feel like I can say a bunch of things now. I can say that f is increasing on 1/4 to the 2/3, comma, infinity, because f prime is greater than 0 on that interval. And we know that f is decreasing on, remember this is the square root of x, so we have no negatives on 0 to 1/4 to the 2/3, because f prime is less than 0 on that interval. And if you're feeling worried about all the stuff in negative land, you could certainly add the sentence that, oh, by the way, the domain of this function is from 0 to infinity. Wait a minute, isn't 0 included? Yeah, there's no derivative there, but the function does exist. And so I'm going to put a bracket on that. Okay, what else do we need? What do we have here? We have min at x equals 1/4 to the 2/3, because to the left of x equals 1/4 to the 2/3, f prime is less than 0, and to the right of x equals 1/4 to the 2/3, f prime is greater than 0. Okay, now, do we have a max? And the answer is yes, we do. We have a domain restriction, remember? This is x equals 0, hard stop. I can't put negative numbers in. And what's happening to the right of that? F is decreasing. So that's a max. So here's the max at x equals 0, because x equals 0 is the left endpoint. And to the right of x equals 0, f prime is less than 0. Nice. So we had a max, we had a min, we had increasing, decreasing, and now we have to talk about concavity. So with concavity, I need to talk about f double prime. So let's take a look at f double prime. This is undefined again when x equals 0. Right? Negative exponent, radical in the denominator. So that's not, yes, I know there's an undefined slope at x equals 0. I think this is all I'm going to acknowledge about that. In fact, when I go to make my f double prime sign chart, I will put 0 on that sign chart. I do want to look at when is f double prime 0. We have 2 minus plus 1/4 x to the minus 3 halves. All right, well, this is a little troubling because when I subtract 2 and multiply by 4, I'm going to have negative 8 equals x to the minus 3 halves. And if I raise both sides to the reciprocal power, negative 2/3. Let's see what that means. So this is cube root of this. Cube root of negative 8 is going to be negative 2. And then negative 2 times negative 2 is positive 4. But, I end up with 1 over 4. And over here, these are going to cancel and turn into 1. X to the 1 is that. And so it looks like I've got this 1/4 here. All right, well, what can we plug in here then? How about, 1/25 was nice last time. 1/9 is fine. But here's what I really want to say. This is under a radical. This can't be negative. It's going to have to be positive times a positive plus a positive. Aren't I always positive here? Like positive, positive kind of thing? So maybe I should test it out and see. Okay, so if I have 2 plus 1 over 4, and I've got square root of x to the 3rd. There's my little f double prime relationship, and I want to plug a number in, like 1. I plug a 1 in there, I have 1/4 plus 2, 2 and 1/4, that's positive. Now, if I plug in something else here, yeah, like a negative 2. Negative 2 to the 3rd is negative 8. I can't take the square root of negative 8. I could put in something like 1/9 to the third. I'll play that game. Yeah. So, okay, I'm giving in. I'm putting in 1/10. So, square root of 0.1 raised to the third power, and that gives me this, and I want 1 divided by, parentheses, 4 times that last answer, and I want to add 2 to that. Well, I get the positive. Yeah, it's just like I said here, positive, positive. It kind of makes me wonder if I really do have that sign change there or not. And so let's take a look at this. This is what our mystery x value is supposed to be. Parentheses -8. And I want to raise that to the -2/3 power. I get, yeah, positive 1/4. Okay. So when I don't have a sign change here, that means I don't have an inflection point, and this function is going from concave up to concave up. So I don't know, maybe it's doing something like that. Let's see what we got going on. I'm going to go back and graph the original function just out of curiosity to see what I've got. X squared minus square root of x. And let's zoom standard. Kind of looks like a parabola. Let's change the viewing mode. Whoa! Oh, I've got a couple of graphs going on here. There we go. Let's go to that one. Is that below? So no, that's not how I change that viewing window. -2, 2. Oh, there it goes. Okay, and there is a min, and there is a max, and yes, this thing is always concave up, but we thought something was going to happen at 1/4, and I don't see anything happening at 1/4 here. But this is. Oh, but there's no sign change. Yeah, but what is happening at 1/4? That's a good question. So I can calculate value 5. That's 1/4. It doesn't look like a critical point. Oh, well, if one of you figures this out, will you let me know? As I sort of feel like that's weird. I know. Let's take a look. See, we've got a calculator. Let's graph the second derivative. I don't want the first derivative, I want the second derivative. And we think 1/4 is an important point on it, so this last viewing window is probably fine, except my x's can't go into negative land, so I'm going to get rid of that and make that a little bigger. Okay, now this is graphing the second derivative. It's going to take a minute, so check your texts. I don't know, but where is it? To not graph. Let's go over to our table and see what values we're getting. Well, isn't that interesting? They seem to be constant. 2s. Or they're very close. Oh, they're different. But they are bigger than 2, the y values. So let's change the y max to something like 5. This is the second derivative. I think that's x equals 1. So 1/4? No. I didn't have anything happening at 1/4. This math here is not correct. Well, let's see, I subtracted 2, I multiplied by 4, and I raised to the reciprocal power. Cube root of that is -2. -2 squared is 4. No, that feels good, but yeah, I don't get any, there are no critical points on f double prime. And that's good, because that's sort of what we were coming to anyway. Does that mean I made a mistake here? The derivative of 2x becomes 2. I bring down that 1/2. Minus 1/2 x to the minus 1/2. Bring that down. That's plus 1/4 to the -3x. Yeah, I like that too. I'm not sure. Okay, yeah. So, like I said, if any of you figured that out, then by all means, please let me know. Because right now, all I can say is f double prime is greater than 0 always. So, therefore, f is, I'll give up always. And we didn't have any inflection points, no IP, because no sign change in f double prime. Okay. Oh, look, some more help. You know, when I look over at 13, well, that's just going to be 1 plus sign. So, 12, you're killing me. 12, f equals x over x squared plus 2, which is x times x squared plus 2 to the minus 1. So f prime, product rule, this times the derivative of that. Don't forget to subtract 1. Don't forget to take the derivative in there. Don't forget you're doing product rule. This times the derivative of that. Okay, factor out the smallest power. So f prime, we're going to take out in x squared plus 2 to the minus 2. And what else will we have? Well, here I'm going to have negative 2x squared. And here, since I took out minus 2, I'm going to have plus x squared plus 2. Okay, so that's going to be negative x squared plus 2 and x squared plus 2 to the negative 3. There's f prime. Well, this is never 0, right? It's a parabola shifted up 2 places. That's never getting down to x equal and y equals 0. So this is always positive. This is never 0. But this could be equal to 0 when x squared equals 2 or x equals plus and minus root 2. So, negative root 2, positive root 2. This is always positive. So I'm just going to know that that's positive. If I test a 0, 2 on top, positive on the bottom, I get a positive there. If I plug in something over here, this is between 1 and 2, 1.41, so I'm going to plug in a 2 and a negative 2. If I plug in a 2, again, this is positive for all x values. You don't have to worry about that. That's positive, positive, positive. But here, if I plug in a 2, 2 squared is 4 times negative minus 4 plus 2 is negative 2. And a negative divided by positive is a negative. And if I plug in that negative 2, well, negative 2 is going to get squared for positive 4 times negative 1, negative 4 plus 2. Again, I got that going on. So here's my f prime sign chart, and I can say that f is decreasing on negative infinity to negative root 2 union root 2 to infinity, because f prime is less than 0 on those intervals. We know that f is increasing on negative root 2 to root 2 because f prime is greater than 0 on that interval. Okay, and can we say anything about maxes and mins? You've got a min here, you've got a max here, and I would expect you to be comfortable in writing those justifications. And I can't believe I erased the rest of it. Oh my god. Yeah, Sorry, Tiger Kukla is not doing concavity on that. But you need to know how to do concavity, so please, please, please practice. Okay, 13, we've got f equals x plus sine x and a bounded interval. F prime is going to be 1 plus the derivative of sine is cosine. And when I think about that graph, cosine starts high, goes low, and back high again. And this is going to be at pi, and this is 0, and this is 2 pi. Okay, so f prime, I know that cosine x equals -1 when x equals pi. So I get a critical number. Yeah, because that's f prime. F prime equals 0 in this situation. What about here and here? I would have thought at 0. Cosine of 0 is 1. Plus 1 is 2. Oh, no, not here. Huh. That's very interesting. What am I missing? At 0. Cosine of 0 is 1. No, that's good. Oh, it's because of this. I'm graphing this. This is the derivative graph. The second derivative has zeros here, here, and here. Not the first derivative. The first derivative has only 1 0 at x equals pi. And that's what I'm looking at. Okay, so I've got my f prime sign chart with pi, 0, and 2 pi on it. And what I notice here, if I plug in a pi over 2, cosine of pi over 2 is 0. 0 plus 1 is positive. And if I plug in over here 3 pi over 2, cosine of 3 pi over 2 is 0 plus 1 is still positive. So that seems to suggest no sign change, that the function is increasing and then continues increasing. You know, increasing, 0 slope, increasing, that kind of thing. So, yeah, I had neither a min nor a max there, but don't forget, endpoints of a bounded interval. So from this point, f prime is positive, which means f is increasing, which means I have a min here. And f prime is positive, which means f is increasing until we get to this point. And so that's a max. Okay, can you write those justifications? I hope so. F is increasing on 0 to pi, union pi to 2 pi, because f prime greater than 0 on those intervals. And if you want a reason why, and it's because this is y equals x. Y equals x is going. Sine plus y equals x is kind of looking like that kind of a thing. So, yeah, it doesn't surprise me that I'm told this function is increasing everywhere but at pi. Okay, no max, no min. Endpoint x equals 0 is a min on f, because x equals 0 is the left endpoint, and f prime is greater than 0 to the left of x equals 0. And I would expect you to be able to write the justification for the max over here at 2 pi. X equals 2 pi is a max on f, because x equals 2 pi is the right endpoint, and f prime is greater than 0 to the, that probably should have been to the right, but I'm now going to the left of x equals 2 pi. Okay, do not erase everything. You still need to do a second derivative. Okay, second derivative. The derivative of cosine is minus sine. Okay, so when is sine equal to 0? Sine is equal to 0 at x equals 0, pi, and 2 pi. And that's what we were seeing on that cosine graph. We were seeing that 0 slope at 0, at 2 pi, and at pi. This was my f prime graph. But I saw all those slopes, and they're 0 slopes, therefore on f prime, therefore there's x-intercepts on f double prime. So we've got 0, pi, 2 pi. If I plug in something here, like pi over 2, sine of pi over 2 is positive 1, times negative is negative. If I plug in a 3 pi over 2, sine of 3 pi over 2 is negative 1, times negative, I get a positive 1. So I see a sign change on f double prime, therefore I have an inflection point. F has an inflection point at x equals pi because f double prime changes sign at x equals pi. Concave up, concave down. F is concave down on 0 to pi because f double prime is less than 0 on 0 to pi. And we know that f is concave up on pi to 2 pi because f double prime is greater than 0 on pi to 2 pi. All right, there, we did all the bits. Satisfy our curiosity about the point where the mean value theorem is satisfied in each case below. So I'm looking at f of x equals square root of x on the closed interval from 4 to 9. Now, remember, there are two preconditions for the mean value theorem. One is f is continuous. Well, f is continuous on this interval. Not everywhere, I can't plug negatives in there, but f is continuous on this interval. And is f differentiable on that interval? Well, f prime is 1/2 x to the minus 1/2, or 1 over 2 root x. Again, f prime is undefined at 0, but our interval does not include 0. So we've met the preconditions for FTC. Now all we have to do is remember what FTC said. And it said that the slope of the tangent at some point must be equal to the slope of the secant between 2 points on the graph. So f of 9, plug a 9 in there, I get 3. F of 4, plug a 4 in there, I get 2 over 9 minus 4. So I get 1/5. Okay, so what I know is f prime equals 1/5 at least once on this interval. Well, let's replace this f prime of c with f prime. 1 over 2 root x equals 1/5. So I'm going to multiply both sides by 2 root x and by 5. So those will cancel, and I'll have 2 root x here. And those will cancel, and I'll have 5 there. So that brings me to 5/2 equals square root of x. And if I square both sides, I get x equals 25/4. 25/4. Well, that goes 4, 5, 6 times, 6 and a little, and that's certainly within there. Yeah. So, satisfy our curiosity, this is the point. When x equals 6 1/4, the slope of the tangent line will be the same as the slope between 4 and 9. That slope will be the same as this slope at 6 1/4. Okay, and let's do the same thing with a slightly more complicated looking function, number 15. Number 15, we're told that f equals x times ln of x on 1 to 2. So what's f prime? Well, f prime is 1 times ln of x plus x times 1 over x, or ln of x plus 1. Well, I wonder when this is. I mean, I know ln has a domain restriction, no zeros, no negatives. So that's sort of in my brain always. F prime could be equal to 0. Ln of x plus 1, negative 1 equals ln of x. And then I exponentiate and get x equals 1 over e. And you knew that already, right? Because you know the graph. There's our graph of ln of x. Or did I want ln of x plus 1? I think no, because this was the thing that I was wondering about. When does ln equal negative 1? And we know our reference points, e1, and this one is 1 over e negative 1. So when is ln equal to negative 1? At the point 1 over e. Yeah. Okay, so we've got a value. I know that this function is continuous and differentiable on that interval, so I'm not worried about the preconditions. I did get an x value, 1 over e, and what was my slope? Oh, why did I set that equal to 0? No, come on. That's because I did all those increasing, decreasing problems. Now, let's think about this. This is supposed to be mean value theorem. I need to find f of 2 minus f of 1 over 2 minus 1 and set that equal to f prime. So if I plug a 2 in here, I have 2 ln of 2, and if I plug a 1 in there, ln of 1 is 0. So 0 times 1 is 0 over 1. Well, that means 2 ln of 2. And that's the average rate of change between those 2 points. Mean value theorem says I'm guaranteed at least one point where the tangent line would have the same slope. So what was our derivative? Our derivative was ln of x plus 1. So this is the equation I want to solve for x. I'm going to subtract 1 from both sides. Equals ln of x. And then I'm going to exponentiate. So I get x equals this number. Now, it may be worth our time to so here's what I'm thinking. When is it that I subtract exponents? That's when I'm dividing. And I could kick this up with the power rule and be 2 squared or 4. So e to the ln of 4 over e to the 1. Now, when the bases are the same and we're dividing, we can subtract the exponents. That's why that's a minus 1. E to the ln, those cancel. So I end up with 4 over e here. That's much nicer than what I was looking at. Do you have to simplify? No, but you do have to solve. So this, I think, would be fine and free response. Yeah, fine and free response, especially if it's a no calculator question. All right, so we used MBT. That's fabulous. Oh, wait a second. 4 over e. I just want to check to make sure that's on that interval. 4 divided by e. And I get 1.47. Yes, that is on that interval. Because if I didn't check, and it turned out that that number was 3.5, and this is my interval, oh no. No, we don't have such a place on our interval. Okay, 16. Use the graph of f prime below to determine when f is concave up, when f is increasing, and when f has maxes. And this is a graph of f prime. And it looks like it says A. I've got a max here at B. I'm going to come down and back up. That's B, that's C, and D, and B. And this is a graph of f prime. Okay, when is f concave up? Well, f is concave up when f double prime is greater than 0 And since f double prime represents the slopes on f prime, in order for the slopes to be greater than 0, then the slopes have to be positive, which means f prime is increasing. And that's happening here on A to B, union here, and on D to infinity. Okay. So that's concave up, is when f is concave up. Concave up, we did that one. When f is increasing. Well, f is increasing when f prime is greater than 0. So that's going to happen at negative infinity to A union A to C union E to infinity. Okay? Those are the places where f is increasing. And finally, where does f have some maxes? Well, this is a graph of f prime, and let's think about it this way. A f prime, C, and E. So what I see is to the left of x equals A, f prime is positive. To the right of x equals A, and to the left of x equals C, again, f prime is positive. Between C and E, however, f prime is actually negative. But after E, we have positive again. So, do I have a sign change on f prime at x equals A? No. So that's neither a min nor a max. How about over here at x equals C? Oh, I go from positive to negative, and so I have a maximum there. And then after that, where we go from negative to positive, that's not a max, that's a min. So the only max I have here is the max at x equals C. Okay, and what would my justification be for that? Same. F has a max at x equals C because to the left of x equals C, f prime is greater than 0, and to the right of x equals C, f prime is less than 0. All right, 17. 17 is the last one. Yay! We learned some calculus. Here's another graph of f prime. That goes up, down, and back again. So this point is called B, this point is called A, this is C, D, E, F, and G. All right. Use the graph to determine when f is concave down. F is concave down when f prime is decreasing. So B to D, union, more decreasing, F to G, hard stop. All right, that's the concave down. That's part A. Part B, decreasing. Well, the f is decreasing when f prime is less than 0. And that happens here on C to E. Part C has mins. Well, think about this as my f prime sign chart with plus, minus, plus. I'm looking for a minimum. Here we go. As f prime goes from negative to positive, we have a min. When we go from positive to negative, we have a max. And this seems to be a bounded function. So don't forget the endpoints. From here, f prime is positive, which means f is increasing, which means this is a min. And over here, this function is increasing until we get to g, and so this must be a max. All right, we're only looking for mins. I've got 2 of them, and don't forget to write those justifications. And what about inflection points? Well, I know inflection points, or x equals a and x equals e. And you write the justifications. And then for this last question, when does f have any inflection points? Well, f has an inflection point when there's a sign change in f double prime. And what I'm looking for is when f prime goes from increasing to decreasing, for example. Because if I look at f double prime, f double prime is going to be 0 at b and at d and at f. And in between these two, f prime is increasing, which means f prime has positive slopes, which means f double prime is positive. From b to d, f prime is decreasing, and because f prime is decreasing, f prime has negative slopes, which means f double prime is negative. From d to f, we see f prime is increasing again, therefore f double prime is positive, and from f to g, we see that f prime is decreasing, and therefore f double prime would be negative. And so I can say that I have inflection points at b, d, and f because f double prime changes sign, works some years, but some years you have to say instead f has inflection points at x equals b, d, and f because you were given f prime, so you should address f prime in your justification because f prime goes from increasing to decreasing or decreasing to increasing at those points. And that really is, in fact, the answer they expect. They want to hear that. They do not, some years f double prime, great, we'll take it. And then other years, sort of capriciously, they say, yeah, no, we're not going to take that this year. They have to talk about f prime. So just be in the habit, if you're given f prime, use f prime to write your justifications. All right, so what do I say in the end? Well, I say if you skip the first two problems, this isn't unreasonable at all. This is a great set of problems to be comfortable with. But maybe we should move those first two problems to the end because they're kind of demoralizing, if not in the least time-consuming. I hope this was helpful, and I hope you have wonderful success on your Chapter 5 test. Take care, everyone.